Okay, this last section in Chapter 3 is called the Fundamental Theorem of Algebra, a very important fact, first proved by famous mathematician Gauss. And we're going to take off on something that you're probably familiar with. If you have a quadratic equation and you have a complex root, a plus bi, then a minus bi is also a complex root of the same quadratic equation. If you think about the quadratic formula, you can show that directly. Otherwise, you can show algebraically through this exercise that you can show this just by performing the operations on this number and plugging in here and showing that if this is a solution, then this is also a solution. Okay. Now you can actually generalize this result for higher order equations. For a quadratic equation, of course, you can write down the quadratic formula. For higher order equations, you can't write down any formula, but you can still prove that if you have a complex solution of an algebraic equation, the complex conjugate is also a solution. Now, the caveat here is that that equation must have real coefficients. Okay, if you have an algebraic equation with real coefficients and you have a complex root of that equation, then the complex conjugate is also a root. Okay, so here are some more exercises along those lines. And we're not going to prove that, but this is related to the fundamental theorem of algebra. The statement is here. Basically, any nth order algebraic equation in the variable z, nth order means that the largest power is z to the n, and it has real coefficients, then there exists at least one and at most n distinct complex roots to that equation. And then here, some more exercises about that. So this is a very brief video to introduce the contents here. All right, that's it.